Next, let's look at how blockchains work. As you know by now, blockchain technology creates a secure, decentralized, or distributed append-only ledger that's maintained through multi-party consensus. As such, blockchain technology seems perfectly suited for verifying the electronic transfer value without the need for a financial intermediary. This audible database or record of transaction uses blocks that are linked to previous blocks via cryptography, specifically hash functions and digital signatures. And this cryptography is tamper-resistant, but not tamper-proof. The reason that faking a block is almost impossible is that the validity of the block, and by extension its inclusion onto the blockchain, is determined by an electronic consensus of nodes. There are thousands of these nodes scattered all over the world, so as a consequence, capturing the network would require a computer with impossible power. Let's talk about digital signatures first. Much like someone might use a handwritten signature to mark their agreement to a document, transaction, or to prove their identity, a digital signature is also used the same way. In order to make the process robust, a signature should be difficult to forge but easy for anyone to check. And just like a very simple handwritten signature might be easier to fake compared to a more complicated one, cryptocurrency digital signatures use a system of two related keys, a private key and a public key, to make sure that the ownership of the cryptocurrency is very difficult to forge. This key pair are used together to encrypt and decrypt transactions. The public key can be thought of as the identity of the owner, and the private key can be thought of as secret information that allows the owner to prove their ownership of the public key. This technology of public and private keys is called Public Key Infrastructure, or PKI, and has been around since the 1970s, and has been used to manage identity and security in Internet communications. To understand how it would work in digital signatures, you must first know how it works with encryption to guarantee message security. For example, if you want to send your friend an encrypted message and your friend's public key is available for anyone to see, you can use your friend's public key to encrypt your message to him. Observers might be able to see or intercept the encrypted message, also called ciphertext, but they will not be able to decrypt the message unless they have your friend's private key as well, which should be only known to your friend. This way, you can rest assured that your friend is the only one who can see the original message in its unencrypted form. A digital signature is something that you can use to show that you know the private key connected to a public key without having to reveal the actual key. So if anyone needs you to prove that you have the private key for any specific public key, you can prove it by supplying a digital signature. This prevents you from giving away your private key every time you need to decrypt data, as someone can take your private key and unlock everything associated with your public key. So in essence, it reverses the operation of the public and private keys in our message analogy above. You can use your private key in a signing algorithm to create a specific signature linked to the specific message and public key. No one can derive your private key from the digital signature. And because the digital signature is created using your private key and the original data itself, every digital signature is unique to that piece of data or that transaction. Hence, if someone tries to use a digital signature in a different transaction or data, it will conflict with the transaction data and not match the one inside the digital signature. By using the correct digital signature with the specific transaction data plus your public key, anyone can run through a specific algorithm to confirm whether a legitimate private key was used to create that digital signature without needing to know your private key. These algorithms use various computational methods to generate random numeric combinations of varying length, so they cannot be exploited with a brute force attack. This pair of keys basically allows one key to validate what the other key does to prove legitimacy. Next, I'm going to explain what hash functions are. A hash function is a mathematical function or algorithm that simply takes a variable number of characters called a message and converts it into a string with a fixed number of characters called a hash value or hash. For example, I've constructed a table where a few different inputs have been run through a simple hash function called SHA-1 to produce an output with a fixed amount of characters. Please note a few things. Firstly, regardless of the length of the input or message, the output or hash value always has the same number of characters, in this case, 40 characters. The second important thing I want you to make note of is that even a small change in the input, such as adding a 1 to the fourth message, causes the hash value to change completely. Also, these hash functions are deterministic, meaning that every time you put in the same input, it will always create the same output. And while it is quick and easy to compute the hash value if you know the input or message and go from left to right in the chart, it's very difficult to go through the process in reverse to compute the input if you only know the output or hash value and go from right to left in our table. The only way that you can compute from right to left is called a brute force search, using trial and error to find a message that fits the hash value and see if it produces a match. A simple way to try to understand hash functions is to think about the difference between squaring a number and solving for a square root. Squaring a number is much easier than trying to figure out the square root of a number, which requires you to continuously guess until the exact number is found. However, once someone gives you the answer to a square root, it's very easy to verify. Hash functions, like the SHA-1 that I've illustrated above, are the basic tools of modern cryptography, and they're used in information security to authenticate transactions, messages, and digital signatures. In other words, any piece of digital information, like a file on your computer, a photo on your smartphone, or a block on a blockchain, has a hash, and each hash is unique to each piece of data. Any small change in the underlying information will lead to a completely different hash.